Welcome, Year 11. This is your mock run-through of your Combined Science higher paper. You need to get yourself a green pen and make your corrections as I go through the answers. Question number 1 says, in an experiment, powdered calcium hydroxide was added to dilute hydrochloric acid and the pH was measured, and then it gives you a method. It says, state what should be done after step 2 to make sure that any reaction is complete. Well, step 1 was measure out the dilute hydrochloric acid into a beaker, and step 2 was add 0.1 of powdered calcium hydroxide to the beaker, and then find the pH of the mixture. Well, to make sure that the calcium hydroxide has reacted, you need to stir it or mix it. It did allow heat it, or warm it, but clearly when you're adding a powder to a liquid, you need to stir it to make sure it reacts. Part B says, complete a word equation for the reaction. Calcium hydroxide plus hydrochloric acid. Well, hydrochloric acid is an acid. Calcium hydroxide is a base. And an acid plus a base gives salt plus water. Now, you can remember that by BASHO, B-A-S-H-O, base plus acid gives salt plus water. So the salt, it's hydrochloric acid, so it's got to be a chloride salt, and the metal is calcium, so it makes calcium chloride. And you got 1 mark for calcium chloride, and the second mark was water. Part C says, which row of the table shows the state symbols for powdered calcium hydroxide and dilute hydrochloric acid? Well, it says it's powdered calcium hydroxide, so calcium hydroxide has got to be a solid. And acids are aqueous, they're not liquids. So you had a choice between C and D, and C was the correct answer. And D was the incorrect answer because acids are aqueous. Part D shows some results of the experiment on a graph. You've got the mass of calcium hydroxide along the bottom, and you've got the pH up the side. It says use figure 1 to give the pH of the acid at the start of the experiment. Well, the start of the experiment was when you hadn't added any calcium hydroxide, and the acid is going to have a low pH, but it's down here. Now, each one of these squares is 0.4 pH units, and this is 0.4, 0.8, and then 0.2. So it's 1. It's got a pH of 1. It's halfway between 1 and 2 on that scale. So they allowed anywhere between 0.9 and 1.1, but the pH was 1.0. It says, using figure 1, give the mass of calcium hydroxide required to make a neutral mixture. Well, neutral is pH 7. If I go along from pH 7, I get to there. If I go down, which is down that line, it's going to be here, and that is 0.74, because along here each one of these lines is 0.2, so 0.72, 0.74, 0.76, so it is 0.74. And that line was actually on that line, so they didn't allow any error in that. It had to be 0.74. Now, the last part of that question says, explain why the pH starts off at a low value and ends up at a high value. Well, you start off with an acid and you add an alkali to it. And if you said that you started off with hydrochloric acid, or hydrochloric acid has a low pH, or hydrochloric acid has lots of hydrogen ions, then you got the first mark. So hydrochloric acid has a low pH, lots of hydrogen ions. Now, when it reacts with the calcium hydroxide, and there I've said it reacts with, that's a key idea to get over, is that it's not just that you're adding an alkali to it, the acid reacts with the alkali, and it is neutralized. It is neutralized, and that got you the second mark. So you could have also said the hydrogen ions in the acid react with the hydroxide ions of the alkali, and they go to give a neutral solution. It is neutralized, and as you add more calcium hydroxide is an alkali, so the hydroxide ion concentration increases, and it's the hydroxide ions that cause it to have a high pH. So you then need to say with excess calcium hydroxide, which is an alkali, high concentration of OH minus, so a high pH at the end. And you need to say those three separate things. Hydrochloric is an acid, and so it starts acidic at the start. It's neutralized when you add calcium hydroxide, and calcium hydroxide is an alkali, so when it's in excess, the pH is high. Question 2 shows you part of the reactivity series, then it gives you some metals, and it says it's increasing reactivity from the bottom to the top. So gold is the least reactive, calcium is the most reactive. Which metal reacts with cold water? Well, that's going to be calcium, the one that's at the top. Only very reactive metals are going to react with water. Obviously, copper, you make pipes out of copper, you do your washing up with a gold ring on, and so these are unreactive metals, the other ones. The next part says a student investigates the reactivity of 4 different metals. A student adds an equal sized piece of metal to each of the test tube. The student's observation for zinc and copper are recorded. It then gets you to make observation for magnesium and iron on the next page. So the easiest way to answer this is to say how much bubbling happens, but you need to say, fizzing can be fast or it can be slow fizzing, bubbling the same. So magnesium, you need to say you get lots of bubbles. And iron, you will get a few bubbles. Now that would get you the 2 marks. You could also say that magnesium gets warm, or it feels hot, the test tube gets warmer. And with iron, it gets very slightly warm allowed. Part 2 says, when metals react with acids, hydrogen gas is produced. Describe a test to show that the gas is hydrogen. If you just put down squeaky pop, you didn't get any marks. You had to say what the test was, and then the second mark depended on the first mark. So you had to say add lighted splint for 1 mark, and then it makes a squeaky pop for the second mark. But if you just put down the squeaky pop test, for example, you didn't get any marks this time. Sometimes you would get 1 mark out of the 2 for that, but this time you didn't, because you didn't say what the actual test was. The test is to set fire to the gas, add a lighted splint to the gas, and if it's hydrogen, it will make a squeaky pop. And part 3, when magnesium reacts with hydrochloric acid, magnesium chloride and hydrogen form, complete a balanced equation for the reaction. Well, acid plus metal gives salt plus hydrogen, and it's a symbol equation, so I can't just write hydrogen, but I need to know that hydrogen goes around in pairs. So the formula of hydrogen is H2. Now, in order to balance that, I've got 2 chlorines there, I've got 2 hydrogens there, so I need 2 HCl. So you got 1 mark for balancing it and 1 mark for recognizing that hydrogen is H2. Now, part C says an excess of magnesium is added to some dilute hydrochloric acid of pH 2. The mass of hydrogen gas produced is measured. The experiment is repeated with excess magnesium, but with the same volume of dilute sulfuric acid of pH 1. So the pH is changed from 2 to 1. State how many times greater the concentration of hydrogen ions is in the acid of pH 1 than pH 2. Well, every value on the pH scale changes the concentration of hydrogen ions by 10. It's a logarithmic scale, is the pH scale, and every value is 10 times the previous one. So because it's pH 1, it's actually going to be 10 times greater. As you lower the pH, the concentration of hydrogen ions gets greater because it becomes more acidic. So the answer was just times 10. 10 times. And the second part, it says with an acid of pH 2, the mass of hydrogen produced was 0.005 grams. So with an acid of pH 1, it's going to be 10 times that, which is 0.05 grams, 0.05, 10 times greater. Now, it did allow, if you, for example, said 2 times to part 1, and you multiplied 0.005 by 2, so you gave 0.01 as an answer, then you got the second mark, as long as, so it was error carried forward from the first part into the second part, essentially. But those were the actual correct answers. Question 3 says ammonia is manufactured by the Haber process by the reversible reaction between nitrogen and hydrogen. Write a balanced equation for the reversible reaction between nitrogen and hydrogen to make ammonia. Well, it's got to be a formula equation, a symbol equation, and it gives you the symbol for ammonia, and it also tells you that it's a reversible reaction. So you've got a lot of information in the question. And it also tells you that the 2 things that react are nitrogen and hydrogen. Now, you need to know that nitrogen, the symbol for nitrogen is N2. Nitrogen is a gas that goes around in pairs, just the same as oxygen, chlorine, hydrogen, all go around in pairs. Nitrogen is N2. Now that reacts with hydrogen, and again, hydrogen is a gas that goes around in pairs, so it's H2. So nitrogen reacts with hydrogen, and it tells you that it's a reversible reaction, so you need to draw the reversible reaction symbol, and then you need to write down the symbol for ammonia, NH3, which is given in the question. So if you did all of that, you got 2 marks out of 3. Now, the third mark was for balancing it. So actually, the way that you got 1 mark for the 3 symbols correctly, N2, H2, and NH3, and 1 mark for the reversible arrows. And then the third mark was for balancing the equation, but you had to get that far before you could get the third mark. You had to get the formulas correct before you balanced them. So the third mark, you say, well, I've got 2 hydrogens on this side. I've got 2 nitrogens on this side, so I need 2 nitrogens. So I'm going to put a big 2 in front of my NH3. That gives me 6 hydrogens on that side. And to get 6 hydrogens, I need to put a 3 in front of that. And if you did all of that, then you got 3 marks. Part 2 says, which row shows the typical conditions of temperature and pressure used in the Haber process? Well, this was just learning these conditions, and it's 450 degrees C and 200 atmospheres. So it was D was the correct answer. Now, the last 2 parts, part 3, says in the Haber process, iron is added to the vessel where the nitrogen and hydrogen react. State the purpose of iron. Iron is a catalyst, so all you needed to write down was catalyst. And if you put down that it lowered the activation energy, then you also got the mark. But that was the easiest way to get the mark, was to write down it's a catalyst. The reaction between nitrogen and hydrogen to make ammonia can reach dynamic equilibrium. The reaction gives out heat. So the way I teach my class to do this is that if the reaction is exothermic, it gives out heat, then I get them to write heat in the equation. So plus heat. So the forward reaction is exothermic. Now, the question says, explain how the position of equilibrium changes if the temperature is decreased. Well, the equilibrium rule says that if you lower the temperature, the equilibrium is going to shift to try and increase the temperature. So whatever you say, it says the temperature is decreased. Whatever it does it to increase the temperature. It does the opposite of what is done. So it doesn't matter whether you got it shifts it to the left or it shifts it to right. You should have still got the second mark, which was to increase the temperature. Now, it actually shifts it to the right-hand side because the forward reaction gives out heat. So the 3 things that you could have said, it moves towards the right-hand side. So the equilibrium shifts to right-hand side. You could also say that it shifts to the exothermic direction, and it does that to increase the temperature. Now, regardless of whether you got heat on either side, you should have still been able to say that it did something to increase the temperature, because it always does something to counter the change, to do the opposite of the change that's done to it. So if the temperature is decreased, it's going to increase the temperature. Part B says compound A is a dark brown gas. Compound B is a colourless gas. 2 molecules of A combine with 1 molecule B in a reversible reaction. You are given some equipment. At room temperature, the equilibrium mixture is a pale brown colour. Devise an experiment to show how the position of equilibrium of this reaction is affected by temperature. Now, look, what you're going to have to do is you're going to have to heat the tube up. You're going to have to cool the tube down, and you're going to see whether it changes colour to either darker brown, in which case more compound A is formed, or more colourless, lighter brown, in which case more compound B is formed. So those were the 3 marks. So first mark, 1, put tube in hot water bath, and that got you 1 mark. 2, put tube in ice bath. And then 3, the third mark, was observe colours. Now, it wasn't good enough to just say and record the colour that it went. You need to say that it will either go darker brown or, and then it says lighter brown or colourless. Lighter brown or colourless. So that was really quite an easy 3 marks. Many people were able to say heat it up by putting it in a hot water bath or cool it down by putting it in an ice bath. And then you weren't quite sure what to say with the colour change because you don't actually know whether it's going to go darker brown when it's hot or lighter brown when it's hot. But as long as you say it should turn both of those colours, then you got the 3rd mark. Question 4 says, a student investigates the mass of copper produced when copper chloride solution in a beaker is electrolyzed using inert electrodes. Where is copper formed during the electrolysis? Well, copper forms positive ions, Cu2+. It's a metal. All metals form positive ions. Now, you then need to know the charge on the electrodes, which is panic, P-A-N-I-C, positive, anode. So the positive electrode is the anode. The negative electrode, negative, is cathode. So the copper 2+ ion is going to go to the negative electrode because opposites attract. So it's going to go to the cathode. So the answer is C, at the cathode. And it then says, a student investigated the change in mass of copper formed when the current was altered. And it gives you some results. And it says, state and explain the trend shown in these results. Well, the state is just how are the two linked. And you can see that as the current increases, then the mass of copper formed increases. And you got 1 mark for the state bit of the question, but the 2 marks with it for the explain. So the state, as the current increases, the mass of copper also increases. Now, the reason why, if the current is increasing, then there are more electrons flowing around the circuit. And so there was 1 mark for identifying electrons. And then if there's more electrons, then there's going to be more copper ions turning back into copper metal. So there's more reduction happening, or there's more ions turning back into copper metal. That's the idea that they're in order to turn the copper ions back into copper metal, they need to gain electrons. So more current results in more electrons flowing. This results in more ions being reduced. at the electrode. And I think that there are some different ways that you could say that, but that's probably the best way to get those marks. Part 2 says describe after the power how after the power supply has been switched off, the mass of copper formed can be measured. Well, lots of you said scrape the copper off, and you didn't do that. You did this. This was a core practical, and what you did was you weigh the electrode before, and you weigh the electrode at the end, and you subtract one from the other, and that gives you the mass of copper on the electrode. Now, before you do that, you need to dry the electrode, and you did that by dabbing it with a paper towel. So the first mark was for saying dry the electrode. And then weigh it and subtract the mass of the electrode at the start. Part C says, in another experiment, 7.4 milligrams of copper is formed. Calculate the number of copper atoms in 74 milligrams of copper. Well, the equation that I taught you to learn was that the number of atoms equals the Avogadro constant times the number of moles. So atoms equals moles times Avogadro number, and the moles equals grams divided by rams. So what you need to do is you need to take your 74 milligrams and you turn it into grams. Well, a milligram is 1,000th of a gram, so you need to multiply it by divide it by 1,000 to get grams. So 74 divided by 1,000 equals 0.074 grams. That was the first mark. And then to get the moles, you divide the grams by the rams. Well, in this case, it gives you the relative atomic mass of copper is 60. So 0.074 divided by 63.5 equals, well, that gives a value of 0.001165, 0.001165 moles. And then you want to take that number and times it by 6.02 times 10 to the 23, and you get a value of equals 7.015 times 10 to the power of 20. Now, you know, a quick check on that. If it's asking you for the number of atoms, the answer in a very, it's a very small amount, 74 milligrams, but the answer isn't going to be 3. You know, it's going to be times 10 to the 20 something. And so I'm on the right lines. Now, you've got error carried forward on all of those. So if you didn't know that 74 milligrams was 0.074 grams, you could still get the other marks by multiplying by the RFM. Sorry, dividing by the RFM and then multiplying by Avogadro's number. But really, that wasn't a particularly difficult 3 marks. Question 5 was another base plus acid question, which we've had already. Acid plus base gives salt plus water, and that's Basho, isn't it? Base Basho, base plus acid gives salt plus water. Now, so the other product in copper sulfate, copper oxide is a base. It reacts with sulfuric acid. It's going to make copper sulfate, and the other product is water. During the experiment, a spatula measure of copper oxide, a black powder, is added to warm dilute sulfuric acid. When the mixture is stirred, the black powder disappears and the mixture turns pale blue. The student then adds more copper oxide until the maximum amount of copper sulfate is formed without wasting copper oxide. Explain how the student knows when to stop adding copper oxide. Well, when all of the acid is neutral, then you can't add any more copper oxide, and the copper oxide won't react, and therefore it stays as a black powder. So the solution turns black. Now, the key thing here is that this says explain how the student knows. And so the solution turns black was the first mark, but then you need to say, well, why does it go black? And that is because the copper oxide is in excess. And it's in excess because all of the acid has reacted. So those were the three things that you needed to say. One, the solution turns black. Two, the copper oxide is in excess. And three, all of the acid has reacted. And for reacted, you could also say has been neutralized, has been neutralized. Part C says the reaction produces an aqueous solution of copper sulfate. What is the best way to obtain crystals from copper sulfate from an aqueous solution? Lots of you said heat the solution on a Bunsen burner until dry. Well, you don't heat crystals until they're dry because they can decompose. So the best way is to heat it using a water bath. And that was the correct answer. So the answer was C. Part D says, when water is removed from the aqueous solution of copper sulfate, crystals of copper sulfate are made. Describe how the arrangement and movement of particles changes as crystals are formed from the solution. Well, there were 4 potential marks you could get for this, and you needed to say 3 out of 4 of them to get the 3 marks. Now, the 4 marks were describing the arrangement and the movement of particles in a solution and then in a solid. Now, the fact that this is crystals and the water evaporates, you can ignore all of that. All you need to know is that it's a solution, so the particles are liquid, and then it's a solid, so the particles are solid. Now, in solution, they're liquid, so in a liquid, I've got to say what the arrangement, I call it A, and the movement, I'll call it M, of particles is. Now, in a liquid, the particles move. They move over each other. They can change places. And the arrangement is a random arrangement. You could say disordered. You could say some other things as well, but random is the best way. Now, in a solid, the arrangement is in neat rows would be a way of getting the marks. You could say that they're in a lattice or that they're ordered. So I'll put ordered lattice in rows, any of that. So they're in neat rows, and their movement is there in a fixed position. So you could say they're not moving, although that's not the best answer, but they're in a fixed position, they're not moving, and they're vibrating about the same position, vibrating in same position. Now, like I say, of those four things, 1, 2, 3, 4, you needed to say 3 out of 4 of those to get the 3 marks. Part E says, in the reaction, copper oxide forms copper sulfate. Explain in terms of electrons whether the copper in copper oxide has been oxidized, or it's been reduced, or has not been oxidized or reduced. Well, in copper oxide, I've got Cu2 plus ions and O2 minus ions, and then it turns into copper sulfate, which is also Cu2 plus ions. So the ions don't change, they don't lose electrons or gain electrons, therefore they haven't been oxidized or reduced. So the copper is neither oxidized or reduced because it has not lost or gained electrons. And the last bit, in another experiment, copper sulfate solution with a concentration of 39.875 grams per decimeters cubed is used. Calculate the mass of copper sulfate dissolved in 0.3 decimeters cubed of this solution. Well, the way I would work this out is I would say X grams divided by 0.3 decimeters cubed equals 39.875 grams per decimeter cubed. So X is equal to 0.3 times 39.875, which equals 11.9625, 11.9625 grams. Question number 6, figure 5 shows the structure of the molecule of compound S. Use the figure to deduce the empirical formula. Well, the empirical formula is the simplest ratio of atoms. So wherever possible, you count them down. So you work out the ratio of atoms, and if you go through this, you work out that C equals 6 carbons, H equals 8 hydrogens, there are N equals 2 nitrogens, there is 1 sulfur, and there are 2 oxygens. Now, I can't cancel that down any further because I've got 1 sulfur. I mean, all of the others I could cancel down, but because I've got 1 sulfur, I can't cancel it down. So that the molecular formula is the empirical formula. So the empirical formula is C6, and you need to write this down as a formula: H8N2S1. Sorry, that's a small one. S1O2, and that was really a straightforward 1 mark. And the second part, the melting point of 3 samples of S are shown in 6. State whether each of the samples ABC is pure or impure and justify your answer using the information in figure 6. Well, if they've got a range of melting points, they're going to be impure, and if they've got a single melting point, then it's going to be pure. So A and C, A and C are impure because the melting point is over a range, and then B is pure because it has a single. Now you could say sharp, it only has one, it has a unique, all of those things. It has a single melting point. And the 3 marks were identifying A, C and B correctly, and then 1 mark for saying that there was a range and 1 mark for saying that it was just one melting point. Part B says a scientist used chromatography to investigate compound S. In the conditions used, compound S has an RF value of 0.22. Well, the RF is a fraction, and it's going to be the small number over the large number, and the small number is going to be how far the compound is gone, and the large number is going to be how far the solvent has gone. Calculate the distance the spot of compound S moves if the solvent front has moved 2.4 centimeters. So if X is the distance that the spot is moved, divided by the distance that the solvent moved, which is 2.4, is going to equal the RF value, which is 0.22, which means that X, the distance that the dot has travelled, is going to be 0.22 times 2.4, which is equal to 0.528, 0.528, or 0.3 if you rounded it up to two significant figures. Part C was the 6-mark question. It says a solution of sodium chloride in water needs to be separated to obtain a sample of pure dry sodium chloride and a sample of pure water. Figure 7 shows the boiling points of sodium chloride and water. Explain this difference in boiling points in terms of the structure and bonding of sodium chloride and water, and how this difference is used to choose a method to separate sodium chloride solution into pure dry sodium chloride and pure water. Well, it was split up like this. This is the indicative content, and you got 1/3 of the mark for describing the structure and bonding of sodium chloride. That's 2 marks. You got 2 marks for describing the structure and bonding of water, and then 2 marks for describing the separation technique. So if we look at this in a little bit more detail, sodium chloride is an ionic compound. It forms a giant lattice between positive sodium ions and negative chloride ions, which are held together with strong electrostatic attractions. And you need lots of heat energy to overcome those strong electrostatic attractions. Therefore, it has a very high boiling point. Water, on the other hand, is a simple covalent molecule. It forms strong covalent bonds in the atoms, holding the oxygen and the hydrogen together. It forms weak forces of attraction between the molecules of water, which need little heat energy to overcome, and therefore water has a low boiling point. And 100 degrees C, in this case, is a low temperature. Now, water boils a lot easier than sodium chloride boils. Therefore, you can use fractional distillation. Now, you can actually, you don't need to use fractional distillation. You can use just simple distillation or distillation with a condenser. Fractional distillation is used to separate 2 liquids with similar boiling points. Now you've got essentially a liquid and a solid dissolved in that liquid, and you can use just simple distillation to separate them. So you need to heat the solution up, and the water will boil at 100 degrees C, but the sodium chloride won't, and therefore the water turns into a gas. You then need to condense it and collect it in the flask at the bottom. Look, I think that was a pretty easy 6 marks. If you understood the topic on structure and bonding, and you could describe the difference between the structure of sodium chloride, which is an ionic compound, and water, which is a simple covalent molecule, then that was easy 4 marks. And then the separation technique in topic 3, separation and purification, just distillation to separate the water from the salt. That's it. I think that's enough to for you to improve your marks. The way that the actual marks were awarded was a little bit different than this, but you don't really know that. I think with the indicative content, you should be able to improve your marks so that it's the best possible answer it can be.